Good afternoon, everyone. So we are in our live session. This is the first live session for the course Mechanics of Solid. And as of now, we have covered 8 weeks. And we started our discussion with 2D stress analysis. And from that basic definition, then we covered 3D stress analysis. So you have seen how the stresses are quantified in 3D. And from the 3D stress field, how we can find out the principal directions, right? Now, these principal directions are extremely useful along with their direction cosines. And for that, we need to do an eigenanalysis, right? Now, besides this eigenanalysis, we have also discussed how to find out stress in a particular plane whose direction cosines are given, right? If you recall the Cauchy's formula, then you can remember how we can resolve the 3D stress tensor into a particular plane where we'll have normal and shear components, right? Then we also define hydrostatic and deviatory components and the octahedral planes, right? That was more or less there in the stress analysis. And the moment you have a 3D stress field, you can also draw the Mohr circle. In fact, we have discussed Mohr circle in 2D and Mohr circle in 3D. Once we discuss 3D stress analysis, then as a special case, we also discuss plane stress analysis, because in engineering, very often we encounter plane stress and plane strain. Now, for plane stress again, it is effectively a 2D analysis. And for that, we have also drawn Mohr circles, and we have solved different examples how to apply those mathematical concepts to solve some engineering problems, right? So once we discuss the stress models, then we moved over to strain analysis. Now, in the strain analysis, you have seen we start with the displacement field, right? The moment you know the displacement field, you can define the strains, different components of strains in the strain tensor. And just like we did for stress analysis, the similar eigenanalysis we also did for strain analysis, and we evaluated principal strains, right, along with their directions. Now, here also you can find out the strain at a particular direction, if you recall, along a straight line, and then within an elastic body, if that straight line moves to a different orientation, then for that orientation also we can find out the direction cosines, right? And in case of strain analysis also, we have plane strain problems, because a lot of engineering problems fall within this category, plane stress and plane strain. And that actually reduces the problem size, and it becomes very handy to solve the problem, and we can reduce the computational cost. Now, once we discussed how to model strains, then one of the most important relation in strain analysis is the compatibility condition, if you recall. The reason is, from the displacement field, you can easily evaluate the strain field, but from the strain field, it is, of course, we can evaluate, but we have to maintain certain compatibility conditions, because if you recall different displacement components, for example, Ux, Uy, Uz, that you can evaluate from the strains. And very often we measure strain, and that's the reason from strain, once we try to get the displacement field, then we need to develop this compatibility condition. Now, once these models are ready, then we had to correlate stress and strain, just like if you have a 1D problem, if you have a bar, that very often we test in the laboratory to find out the Young's modulus of a material. There we correlate stress and strain using Hooke's law. Now, when you have 3D stress field and strain field, And if you try to correlate them, obviously you'll have a number of material constants. Now, once you assume your material to be homogeneous, elastic, and isotropic, then the number of constant reduces to 2. These are called Lami's constant, right? And these are, if you recall, mu and lambda. These are the two Lami's constants, right? Now, when you deal with the material, you can test it in the laboratory and you can easily find out what is the Young's modulus and Poisson's ratio. And from that information, you can actually find out all other material constants that we need to model stress and strain, right? And we also discussed what is the relation between stress and strain when we have a homogeneous, elastic, and isotropic material for 3-dimensional case, right? Then once we correlated stress and strain, we discussed different failure theories. They are extremely important because our ultimate objective is to design a structure, and for designing a structure, we have to combine different components of stresses, and ultimately we'll get a kind of failure conditions that we always verify in our design process, right? And if you recall, out of different failure theories, we discussed Tresca particularly and von Mises. These are the two different yield conditions. They are heavily used in the design, and what are their rationale behind their formulation, that we also discussed, right? So that tells us how the failure for a material, so what the stress and strain analysis is concerned, is defined, right? And in fact, we in this course dealing with linear material, and for our analysis, crossing the yield point of a material is what we call failure. And yield point also for a particular material, we can easily find out if, of course, the material is ductile, we have a distinct yield point. These issues also we discussed at the very beginning of the course. Now, once that is covered, that constitutes the first module of this course. Then we went to the second module. And in the second module, we have bending stresses in beams, right? So we started with how the bending stress is distributed over a cross section when a beam undergoes bending. Then we have noticed that for our type of structures that we are dealing with, the bending stresses linearly vary across the cross section. We define the neutral axis over which the stress is 0. And as we move away from the neutral axis, our bending stress linearly increases. And at the extreme fiber, we have maximum bending stress. Now, depending upon the type of bending, which may be hogging or sagging, we can have tension at the top or tension at the bottom, right? Likewise, we'll have compression at the bottom or compression at the top, depending upon the type of bending that we wish to model in our analysis. Then we derive the relation between the bending stress and the curvature of the material of the beam undergoing bending deformation. And we also derive the expression for the displacement during bending, right? If you recall, EI d2y or d2u dx2 is equal to minus of mx. That is the moment applied at a section x. Now, from this equation, we can find out the displacement field using double integral, right? And if we have a uniformly distributed load or a load covering the entire domain, we can easily use this concept and find out the displacement field. But very often we have combinations of different types of load, mostly point loads and patch loads. And for that, again, we learn Maculus method. Now, Maculus method is very useful. Using this, effectively, it's a double integration method. But in this method, we can consider any general type of loading, and then we can also solve for the displacement field of a beam that is undergoing shear bending. Now, this analysis is particularly useful because very often we encounter beam design in civil engineering, and therefore we need to know how the stresses are distributed across the section of the beam. With that background, then we also define how to apply compatibility conditions, and using that compatibility conditions, if we have two different materials forming a beam section, then what is their capacity? We use some examples. We solved some examples with wooden beam and having steel plates as cover. For that, we defined modular ratio. Modular ratio is nothing but the ratio of the Young's modulus of the material to different materials. Here, in our examples, we considered wood and steel. So using the Young's modulus of these two different materials, you can find out the modular ratio, which is the ratio of Young's modulus. Now, what is the utility of this concept? Because using this modular ratio, you can either convert the wood steel section into an equivalent wood, or you can also convert it into an equivalent steel. Likewise, if you have any two different materials, or more than two actually, then you can use the same concept and you can convert them into a uniform section having a single material, and then you can find out the sectional capacity. We also studied bending stress distribution across built-up sections, and there also we noticed that the bending stress distribution is linear, but of course, depending upon the type of built-up section we deal with, there we have to locate the neutral axis first, and with respect to the neutral axis, then we draw the shear stress distribution across the section. Then, bending stress distribution across the section. Then we also derived the expression for shear stress distribution. Now, shear stress distribution actually considers variation of bending moment along the length of the beam, and we try to find out the unbalanced moment, and that unbalanced moment creates a force along the longitudinal direction that we balance with the help of shear stress at a particular fiber of the section. Now, using that concept again for the intersection, we can draw the shear stress distribution. And then we also define the concept of shear center, because otherwise, if you have a section which is IXY is not equal to 0, then what happens? If we apply a shear force, that can actually cause a rotation at the section level. But if we apply the shear force through the shear center of the beam, then obviously it will not undergo any type of rotation at the section, right? So we have seen how a circular cross section, which is having shear center at the center, the moment you introduce a cut, then we have a different location of the shear center that we have derived in detail discussion, right? So with that, actually, we have this open session. If you have any query, you please come forward, and then we will try to clear your doubts. In the remaining course, we have energy methods. We will pay our attention on the solution of indeterminate structures, how we can apply the concept of Castiglione theorem and solve the displacement and rotation for any structure. And we can also use those theorem for solving indeterminate structure that we will take up in the following video. And after that, we'll also discuss torsional problems, because in engineering mechanics, very often we deal with torsion. So how to quantify torsional stress for a section. And then again, we'll consider some uniform section, non-uniform section. For non-uniform section, what are the challenges we have? Then if you consider the working, what happens? All this is what we are going to study as we progress this course. And then finally, we'll also talk about the buckling of beams. So with that, we will close our session. But for the time being, up to the solution of beam problems, if you have any query, please let me know. And then we can clear your doubt here. Okay, so let us close our session here. If you another open session for the second phase. In the meantime, you can also reach us through emails and we'll try to clear your doubts, right? Thank you very much.